Hey guys, it's the Math Edumacator here. I know I've been kind of busy these last few weeks with school and all that, but I wanted to make sure I caught you today because it's a very special day. It's Pi Day, March the 14th, because 3.14. So this is a very important day for us mathematicians, and I wanted to celebrate by talking a little bit about pi, and in particular, how we calculate pi. Now, there's all kinds of different ways you can calculate pi. You can do it purely mathematically. There's ways to do it to just get general measurements. For example, you can just take a circle, any kind of like circular object. I've got this little like kind of coaster thingy here, like mouse pad. I don't know what this is, but it's a circle, and so I could measure the circumference of this thing, and I can measure the diameter straight across, and then if I take the circumference divided by the diameter, I should get pi. And so I can do that for this object. I can do that for any number of circular objects I have. I can do it for, say, something like this. Measure across, measure around. There's all kinds of different ways to do that. And it's very likely that the early calculations of pi were done this way. When mathematicians did these calculations, the Greeks, when they did these calculations, at first they noticed, this always comes out to be around the same number. But eventually they did, and I believe it was Archimedes. They did actually calculate very mathematically how to find pi very precisely. And so that's what we're going to talk about today, is how you find pi using polygons. This is where it all began, a circle with diameter 1. Now since the diameter is 1, and we know that the diameter times pi is equal to the circumference, we know that the circumference around the circle is going to have to be equal to pi. So one of the ways that we're going to try and calculate that is we're going to look for parameters of polygons. So let's take a square. And we're going to draw the square inside the triangle, inside our circle, like this. This is called an inscribed polygon, or inscribed square in this case. And we're also going to draw another square outside the circle. So in this case, if I take my blue circle, my blue square and my green square, the blue square touches the circle at the corners, whereas the green square touches the circle on its sides. The blue square is going to have a smaller perimeter. You see, it doesn't cover as much ground. It's actually going to have a smaller perimeter than the circle. And the green square is going to have a larger perimeter. So what can we say about this? What we can say is that the circle is going to be somewhere between the perimeter. It's going to be somewhere between the perimeter of my blue square and my green square. Now, some of y'all might be looking at that and going, that's not very precise. How are we going to actually calculate pi using that? Well, yeah, square is not very precise, but what if we used it with a hexagon instead of a square? See, looks a little bit closer now. The outside hexagon and the inside hexagon look a lot more similar now. So that's going to be a little bit more precise than the square. And I could even do this with an octagon. So now they're even closer together. My two octagons, the green and the blue, are now even closer together. So that gives me even a more precise measurement of pi. There's a theorem in calculus that has a couple of different names, but the most common one is either the squeeze theorem or the sandwich theorem. And so basically what that means is that if I have two functions, if I have three functions, where I've got one big one small one, and one in the middle. But I know that at a certain point, the big one and the small one meet up, or that they have the same limit, that I know that the one in the middle has to be at that exact limit as well. And so the way that we can apply that here is I know that both that as I add sides to my inscribed polygon, it's going to get closer and closer to this circle at the perimeter. As I add sides to my circumscribed polygon, it's also going to get closer and closer to the perimeter of the circle. And so they're going to look more and more like circles until we can get as precise as we want. We can get an estimate of the circumference of the circle that's as precise as we want it. So what that means is we can if we can find the perimeter of these polygons, we can find pi. Okay, so now we get the principle. We know that we're going to take our circumscribed polygon and our inscribed polygon and figure out how to calculate the perimeters of each of those polygons. And then we turn those into a function where our independent variable is the number of sides. And so we can use that to find a function kind of in the middle, which will be our estimation for the circumference of the circle, where as we plug in numbers that get bigger and bigger, that estimation is going to get closer and closer to pi. We're going to start by finding the perimeter of the inscribed polygon, the one on the inside of the circle. So first off, remembering that the diameter of our circle is 1, that means that the radius is simply 1/2. So I can draw my radius of 1/2 from the center of my polygon to any of the edges the corners that lie on the circle. So I can draw these two. Okay? So these are both 1/2. All right? Now, this angle here is how wide this angle is going to depend on how many sides my polygon has. In this case, it's a square, so I have 4. So that means that I could actually have 4 of these same angles going to for each one of the faces. So I have this one here. I could have it going this way. I could have it going that way. I could have it going this way. So this means that I've now cut the circle into 4 parts. Okay, so I would take my 360 degrees of my circle and divide it by, in this case I'm dividing it by 4, but it actually is going to be divided by n because I want to be general, and where n is the number of polygons that I have. All right. So this is all well good, but then the other thing is that I also want to cut this this triangle itself in half. Okay. So now, in addition to cutting it by n, I'm also cutting it in half. So if I take half of this, then that is going to be just 360 divided by 2n, which is simply 180 degrees divided by n. All right. So far, so good. So that tells me this angle here. Now I already know this angle. I know the hypotenuse of my right triangle. Okay. So what I can do is that means that I can use trigonometry to find how long this is. This section here. Now, if I use trigonometry, so I have this angle here is 180 degrees divided by n. Now, I know that for an angle, the sine of that angle is equal to the opposite side divided by the hypotenuse of the right triangle. So what this means is that the sine of 180 degrees divided by n is equal to my unknown side. So let's say that's the side length. So let's call that x for right now. For right now, we're going to call that x. Okay. Now, this to x, my missing side, divided by 1/2. Okay. Well, x divided by 1/2 is simply going to be 2 times x. All right. Now, and this is where you have to be kind of careful, so follow along. If I have 2x over here, what I can do is I can actually take that 2, divide both sides of my equation by 2, so I have just x on this side. So now I have the sine of 180 degrees divided by n, all over 2. That gives me x. Now, some quick clarifications. X is half of one of my side lengths. Okay, so in order to get my whole side length, I would actually need to multiply x by 2. So actually what I'm going to do is I'm actually going to just ignore this here and just use what I have up here. Okay, so that means that 2 times x, which is 2 times half a side length, which is the whole side, is now, we know that that is the sine of 180 degrees divided by n. All right? So that tells me how long one of my sides are, which means that I can actually say exactly how much my perimeter is, because all I have to do is multiply my side length times the number of sides, which is n. So for an n-gon, the perimeter of the inscribed n-gon is n times the sine of 180 degrees divided by n. Next, we're going to find the perimeter of the circumscribed n-gon. So we already have the perimeter of our inscribed n-gon here, just for reference. The way that we're going to solve this is actually very similar to the way that we solved the previous one. So first off, the circle still has diameter 1, which means it has radius 1/2, except this time we're actually our radius actually goes to the side of our polygon rather than the corner. So in this case, I have this. As before, this angle here, or rather, I should say, this angle here, by the same reasoning that we did before, is simply 180 degrees divided by n. So we have 180 degrees divided by n. Okay. Now we want to find this side. You know, the side from here to there. So now we don't know the hypotenuse of our triangle anymore, but we do know the adjacent side. So if I remember correctly, the tangent of an angle is the opposite side divided by the adjacent side. So that means that if I take the tangent of 180 degrees over n, that's going to be equal to my unknown side, which is x, divided by 1/2. Opposite divided by adjacent. And that's just 2x. So we say that x was the length, was this length, half of our side length. then the whole side length is going to be 2x, which means that the whole side length is equal to the tangent of 180 degrees divided by n. And furthermore, that means that if I wanted to find the entire perimeter, I simply take my side length and multiply it by the number of sides, which is n, which means that my circumscribed polygon is going to be n times the tangent of 180 degrees divided by n. Now, some of you, I don't know if all of you are thinking this, some of you might be wondering why I'm using degrees rather than radians. I actually prefer using radians. However, if you use radians to solve this problem, to plug into your trigonometric equations, trigonometric functions, then you actually run into the issue of using pi to calculate pi. So we're going to be a little more authentic and use degrees instead. So now I have my two bounds. I have my inscribed perimeter, and then I have my circumscribed perimeter. So my estimate has got to be somewhere between these two. And so what I'm going to do is I'm going to take the average. I'm going to add these two functions together and divide by 2. And we're just going to call this pi of n, that function, because that's my pi estimation function. Okay? So all I have to do now is I simply evaluate this number at, let's evaluate this function at n, where n is the number of polygons. So we can start with 4. And this one I'll work out by hand, but we won't do that for all of them, as you'll soon see. So 4, so pi of 4 is 4 times the sine of 180 divided by 4 is 45. So the sine of 45 degrees plus 4 times tangent of 45 degrees, all divided by 2. Now, the sine of 45 degrees is 2 squared over 2. Right? So we have 4 times the square root of 2 over 2 plus 4. Now the tangent of 45 degrees is 1, because it's actually the sine over the cosine. The cosine is also 2 pi, root 2 over 2. So root 2 over 2 over root 2 over 2 is 1. So the tangent of 45 degrees is actually 1. Okay, and this is all divided by 2 still. Okay. So now I have, when I do this, I get some cancellation here. 2 and 4. The 4 divided by 2 just becomes 2, so we end up with 2 times square root of 2 plus 4 times 1 is 4, all divided by 2. And finally, the last bit of simplification, I can cancel this out with these two things. So if I cancel out this and reduce that to 2, cancel that out, so I end up with root 2 plus 2. And if I use my calculator, then I can actually figure out what that is more precisely. So let's see. Hopefully you can see here. So if I take the square root of 2, the 2 square root of 2 right there, plus 2, that gets me 3.414. Well, that's not too bad. That's actually fairly close, believe it or not. But like we demonstrated earlier, if I do this for even higher values of n, it'll get even closer to pi. we can plug in bigger numbers. We worked it out with 4, but I wanted to look through some other numbers with you. So right here, I've got Desmos pulled up on my tablet. Here, it's brand new. Don't want to break this. So I got Desmos pulled up on my tablet, and I have the function. Let me see if I can get this in a good angle for you guys. Okay, so I have Desmos pulled up here, and over here, over here, we have the function. Oh, geez, we have the function that I made, and down here, this is our pi estimation function. Now down here, I have I have a number that I can plug into it, and it'll give me the function evaluated at that number down here. And so let me just use my slider a bit. If you don't have Desmos, it's actually really, really nice. So I highly recommend this app, or just using it on your computer. So to start with, let's evaluate at 10. So we plug 10 into our estimation function, and we get, let's see, what number does that come out to be? Okay, so if we evaluate our function at 10, we get an estimation that is 3.1696. Okay, well that's closer than 4. So let's try another one. Let's go a little bit, let's get it even crazier. Let's have how about 20? So a 20-sided. Hold on. Okay. It's taking a little bit to focus, obviously. Okay. So when we evaluated our approximation function at 20, we get this number here. Yep, there we go. Okay, 3.148. Okay, so we've got, actually now we've almost gotten it to 3.14. It's still a little bit high, but we can fix that. Let's bring it up even further. Let's bring it up to 100. So our circumscribed inscribed polygons now have 100 sides. Okay. Okay. And this is actually about as far as Archimedes calculated it. This is why we commonly use 3.14, because this is actually, I believe he did a polygon with 90 sides, no, or 92 sides. And so he actually said, well, it's guaranteed, it's definitely 3.14 something. Okay, so 3.14. Okay, and we can go even further. If we do 1,000 sides, I'm not gonna hold that out. I'm having to wait for it to focus on there, and it's taking a long time. So with 1,000 sides, our estimation is 3.14159523747. Okay, that's even better. What about 10,000 sides? Well, 10,000 sides is 3.14159267942. Sorry, 43. Okay, very nice. Okay, at 100,000 sides, our approximation is 3.14159265385. Very good. At 1 million sides, 3.14159265359. And if I go up any past that, to 10 million, it actually doesn't change. Like what I have written on the tablet actually doesn't change, because it's so close that the only digits they're changing are way far down the chain, are way far in the millions and trillions, millions and billions and trillions digits place. So So we're going to have that. We're going to have those numbers pop up somewhere on the screen for you, just so you can you can see how close they are. And I mean, it's pretty impressive. Like this really is like with a computer that's precise enough. This really is how you just calculate pi forever. Like this literally is how you would calculate pi to any number of decimal places that you want, provided that you have a computer that's precise enough to be as precise as you want it, to measure it to, you know, hundreds or billions of digits. So, I mean, that's pretty much it. So, on behalf of the Math Edumacator team, I wanted to wish you all a happy Pi Day. Want more education? Subscribe to the official Math Edumacator YouTube channel and follow us on Twitter at Math Edumacator. See you next time. Oh, and have a totally radical day. One last thing. In keeping with the best of Pi Day traditions, don't forget to treat yourself as well as your mind. See you later.